Welcome back to the next video, everybody. Today's video will be on Mazur's lifting conjecture, and we are on chapter 6 of my notes discussing Langland's tunnel and how it is used in the proof of Fermat's last theorem. So a little review first. Let E over Q be an elliptic curve. For a prime P, let rho bar EP be the mod P representation attached to E. We talked about that in chapter 1 of my notes far back in the series. Let's recall here, though, two crucial properties of rho bar EP. We'll let omega P from the absolute Galois group of Q to F cross P be the mod P cyclotomic character, which is the character encoding the action of GQ on the Pth roots of unity mu sub P. Then we'll just recall that the determinant of the representation rho bar EP is omega sub P. In other words, rho bar EP has cyclotomic determinant. In particular, it's odd, and so the determinant of complex conjugation is -1. We'll let Q be a prime, and we'll let big Q be a prime of Q bar that lies over Q. Then the trace of rho bar EP at the Frobenius at Q is equivalent to Q plus 1 minus the number of FQ points on E mod P. For all primes Q, where rho bar EP is unramified, so that means trivial on inertia. Okay. Another way of thinking about this, essentially by Neuranog Shafarevich, is this should be true for all primes Q of good reduction. And yet another way of thinking about this is you can look at all of the primes Q that are unramified in the P torsion field attached to each. That's Q adjoin the P torsion of E. You'll ask if this equation holds for those primes. Okay. All of this was discussed in chapter 1. I'm pretty sure I explicitly discussed number 2. I just can't find exactly where I did that, but I can tell you that you can find it in Diamond and Sherman chapter 9. Okay. Theorem 9.4.1. Okay. So let's recall the statement of modularity. We'll denote by S sub k of gamma 0 n epsilon the space of cusp forms of weight k, level n, and character epsilon. So remember, epsilon here is a Dirichlet character mod capital N, so it's a homomorphism from Z mod n Z cross to C star. Recall that rho bar EP is what we call modular, in parentheses, of weight 2, level n, and character epsilon, but I won't say that from here on out. If there's a new form F with Fourier coefficients A sub n in S2 gamma 0 n epsilon, for some n and epsilon, and a prime lambda in Q bar lying over P, such that A sub Q, so the Qth Fourier coefficient of F, is just equivalent to Q plus 1 minus the number of FQ points on E mod lambda. So in other words, AQ is essentially the same thing as A sub Q of E, okay, for almost all primes Q. And then what did Wiles want to do? His goal was to show that an elliptic curve E over Q is modular. And so what that means, as we've just seen, is he sought to locate a new form F in S2 gamma 0 of n as above attached to E, such that AQ is equal to Q plus 1 minus the number of FQ points on E for almost all primes Q. Okay. And so what does Wiles actually end up doing? Like, this is what he wants to do. So what does he end up actually doing? He ends up proving a special case of the following, which is called Mazur's modularity lifting conjecture. And it says, let E over Q be an elliptic curve and let P be a prime, such that rho bar EP is an irreducible representation and a modular representation. Then E is modular. In other words, well, you can take E being modular to mean what I just told you it meant, or you can think about it as just rho EP being modular as a representation. Okay. So in other words, if rho bar EP is modular and irreducible, then it should lift to a modular rho EP, where rho EP is just the p-adic representation attached to E. So this is why it's called modularity lifting. You're lifting the property of modularity from the residual mod P representation to the p-adic representation. Now, more specifically, what does Wiles do? He proves that modularity lifting is true for P equals 3 and 5, but that's only when E over Q is semi-stable, although it is true in general. That was proven later, though, in 2001, I believe. And he also proves that modularity lifting for P equals 3 and P equals 5, which he gives us for semi-stable elliptic curves, is enough to prove the modularity theorem for semi-stable elliptic curves E over Q. So he kind of does two things. He shows the lifting conjecture for P equals 3 and P equals 5 for semi-stable curves, and then he shows that that's enough to get you the modularity theorem overall for all semi-stable elliptic curves E over Q. Okay, so what's the goal of this chapter? So the overarching goal for this chapter is to explain Langland's tunnel, which has as a consequence that for P equals 3, the second condition of the modularity lifting theorem above somehow follows from the first condition. This is the broken, overpowered miracle, one of them, of the proof of Wiles and Taylor. That is, when P equals 3, somehow this irreducibility here just gives you the modularity for free. You don't have to derive it or assume it or prove it or anything like that. Very miraculous. This seems to be a special feature of the prime p equals 3. Okay? And so the goal, so what's the goal over the next few videos? Because we've already developed several goals here, right? If you watched my last video, there were several other goals introduced. The goal of the next few videos is to just take Langland's tunnel for granted, and I stated the theorem in 2 different forms last video, and just show, assuming that when rho bar E3 is irreducible, it must be modular. Okay? And so I'll start taking care of that next video tomorrow. So I'll see you then. Thanks for watching.